Welcome to AI Paper Slop, where we dissect the latest tech and AI research for you. Today we are looking at ABRA, Scaling Diffusion Image Training, by Kyle Schickering and the team at Luma AI. And we're going to jump right into the core findings because this paper fundamentally rewires how we train vision models.
Yeah, it completely breaks the rules we've been relying on for years.
Exactly. So here is the 60-second blast of what you need to know right now. First, compute optimal scaling for text-to-image confusion models requires roughly 200 image tokens per parameter, or TPP. That is a massive 10 times the established Chinchilla rule for LLMs.
Which is an insane jump in data requirement.
Right. Second, unlike LLMs, diffusion models are incredibly robust to overtraining. You can push a model twice as far past its compute optimal point, and you suffer almost zero loss penalty. Third, generative metrics scale predictably, but they demand completely diverging resource allocations.
Depending on if you want realism or prompt alignment, yeah.
Yep. Fourth, the optimal classifier-free guidance, CFG, actually drops as model size scales up. And finally, compute optimal diffusion training exhibits scaling collapse, which proves there is a universal dynamic for visual models.
And that's something you can literally monitor in real time.
Yeah, so we are going to deconstruct the math and the mechanics behind every single one of those findings today. But to understand why vision scaling breaks our trusted LLM heuristics, we have to look closely at the controlled model family the researchers built to prove all this.
Right, because you can't just assert this stuff without a rock-solid experimental setup. So the Luma AI team created a suite of models called ABRA, and these are dense, flow-matching diffusion transformers.
Flow matching being the key term there.
Yeah, they range from 60 million parameters all the way up to 2 billion. And they were trained across a massive compute scale. We're talking 3 orders of magnitude, from 10 to the 19th up to 10 to the 22nd FLOPs.
And just for the practitioners listening, flow matching is essentially a generalized mathematical framework that encompasses diffusion. So instead of just adding noise and predicting it back, flow matching learns a vector field that continuously maps a simple noise distribution to a complex data distribution.
Right. It's highly efficient, but spanning that much compute with a stable architecture is, notoriously difficult.
Oh, absolutely. I mean, if you've ever tried to scale up a model, you know that finding the optimal learning rate as your matrices get larger, it usually requires incredibly expensive grid searches.
It eats your compute budget alive.
Exactly.
Yeah.
So how did they manage to span from 60 million to 2 billion parameters without burning through their entire budget just, tuning hyperparameters?
So they bypass that entirely by using maximal update parameterization, or MUPI for short.
MUPI.
Yeah. Normally, as your neural network layers get wider, the variance of the activations grows, right? So if you use the same learning rate across different sizes, your gradients will either vanish or explode.
Right. The math just breaks down.
Exactly. But MUPI solves this mathematically by scaling the initialization and the learning rate multipliers so that the optimal hyperparameters remain completely invariant to the width of the model.
So the size doesn't matter for the hyperparameters anymore.
Right. By implementing MUPI, the team found the optimal learning rate on their tiny models, which landed at 4 times 10 to the negative 4, and they were able to cleanly transfer it zero-shot across the entire scaling ladder, all the way up to the 2 billion parameter model.
See, that zero-shot transfer is what isolates the variables so perfectly. It removes all the noise of hyperparameter tuning and just lays bare the actual scaling dynamics.
Yeah, it gives you a perfectly clean signal to look at.
And that brings us to the core finding, the 200 tokens per parameter rule. Because we have spent the last few years living in a Chinchilla world, right? Where the golden rule for language models is roughly 20 tokens per parameter. Right. You balance your compute somewhat evenly between your model size and your dataset size. But ABRA proves that for vision, both dataset size and parameter counts, they still scale symmetrically with compute. They both scale to the power of 1/2, but the baseline token requirement is a full order of magnitude higher.
Right. 200 TPP instead of 20. And the underlying mechanism for that 10x data requirement comes down to the dimensionality of the latent space and, well, the nature of the training signal itself.
Meaning the difference between text and pixels.
Exactly. Text is discrete. A word token has a highly defined condensed semantic meaning. But an image token, like a patch of pixels, is just a dense, continuous grid. The information density of that visual token is entirely dependent on its local context.
It doesn't mean anything in isolation.
Right. Furthermore, the objective function in diffusion is phenomenally noisier. You are mapping random Gaussian noise back to a coherent data distribution. So the batch-to-batch loss variance is just massive compared to, next token prediction in an LLM.
Okay, let's ground this with an analogy for the listener, because I think this is crucial. If an LLM is like a student who can read a textbook on human anatomy once and grasp the discrete concepts, that's your 20 tokens per parameter.
Right.
A diffusion model is an art student. That art student needs to sketch a human hand from 10 different angles, in harsh lighting, soft lighting, and motion, just to understand the underlying spatial and dimensional geometry.
That is a great way to put it, yeah.
The model needs those 200 tokens per parameter because it isn't just learning discrete concepts, it is learning a high-dimensional, continuous probability distribution of how light interacts with matter.
And that maps perfectly to the math of generative probability. And because mapping that probability distribution is so noisy, the optimization surface behaves very differently when you miss the ideal target.
Right, because Chinchilla tells us where the mathematical optimum is. But anyone actually deploying models knows you rarely hit that exact compute optimal target in the real world.
Almost never. There are always budget constraints or hardware hiccups.
Which is where we hit a massive divergence from language modeling. The paper compares the ABRA family to the Gemstone suite, which is an open-source LLM scaling family. And if you push an LLM past its compute optimal point, you get a severe loss penalty.
Yeah, it is a steep, punishing curve. LLMs do not like being overtrained.
But for ABRA, the curve just flattens out. Overtraining a diffusion model is practically free in terms of mathematical loss.
It's actually kind of wild. The data shows that a model overtrained by 2x, meaning it's trained on twice the compute optimal data for its parameter size, it suffers less than a 0.5% relative loss penalty.
Less than 0.5%? That's nothing.
Right, compared to a perfectly optimized model trained on that exact same compute budget. The batch-to-batch noise in diffusion essentially acts as a regularization mechanism. It heavily obscures the effects of overfitting that usually plague LLMs.
Wait, if the loss penalty is less than 0.5%, I have a very practical question for the ML engineers listening. Why wouldn't I just aggressively default to training a tiny, 60 million parameter model on an effectively infinite data set? I could burn my compute budget up front on training and save millions of dollars on inference costs when I eventually deploy the model to users. Is there a catch to doing that?
You've just described the optimal strategy for a compute-limited deployment environment.
So that's literally what you should do.
Exactly. The actionable takeaway here is that you should absolutely err on the side of a smaller model paired with more data. You shift your compute costs from the deployment phase back into the pre-training phase.
Which saves you a fortune when serving it.
Yes. You end up with a parameter-efficient model that is vastly cheaper to serve, and the loss doesn't degrade. The only catch is the other side of the curve.
Undertraining.
Right. While overtraining is forgiving, undertraining a diffusion model like stopping before you hit that 200 PTP mark is catastrophic. The loss curve just drops off a cliff.
Okay, so the math is incredibly forgiving on the overtraining side. But anyone who has actually trained a vision model knows that raw mathematical loss doesn't perfectly correlate with beautiful, coherent images.
No, not at all.
Because loss is just calculating how well we remove noise, right?
Yeah.
So how do the actual generative evaluation metrics respond when we scale up?
This is where we have to deconstruct what we actually mean by visual quality. Because the researchers tracked several standard metrics, specifically FID, KID, clip score, and CMMD. And all of them follow predictable power laws based on compute, meaning they do scale reliably, but their compute optimal allocations fiercely diverge. They demand completely different resources.
Let's unpack those metrics for the listener so this contradiction makes sense. So FID, or Freshan inception distance, and its sibling KID, they basically measure how well the generated images match the real dataset distribution.
You're right, the distribution fidelity.
Mathematically, they use a pre-trained network to extract features from a batch of real images and a batch of your generated images, and then they calculate the distance between those two multivariate Gaussian distributions.
Exactly.
So it's a measure of pure visual realism and texture. On the other hand, CLEP score uses contrastive learning to measure the cosine similarity between the text prompt embedding and the generated image embedding.
So it measures how well the image actually aligns with what you asked for in the prompt.
Right. And with those definitions in place, the divergence becomes pretty clear. The data shows that if you want to optimize for FID and KID, that distribution fidelity, your data set size must grow much faster than your model size.
Yes.
But if you want to optimize for CLA score and CMMD, the semantic prompt alignment, your parameter count must grow faster than your data set size.
And that tension is huge.
It feels like a brutal contradiction for an architecture team.
Yeah.
I mean, to get photorealistic textures, you need an insatiable amount of data to memorize the vast diversity of the real world. But to understand a complex, highly nuanced text prompt and translate that into visual semantics, you need deep internal model capacity.
You need parameters, yeah.
Generating an image is essentially pulling your compute budget in two conflicting directions at once.
It really is. And that tension actually explains the findings around Classifier-Free Guidance, or CFG as well.
Oh, right.
For context, CFG is a technique used during inference. You generate the image conditioned on the text prompt, and you also generate it unconditionally without the prompt. And then you extrapolate away from the unconditional prediction to artificially amplify the text conditioning vector.
It's essentially a volume knob, right? You're artificially turning up the volume on the text encoder, forcing the UNet or the DIT to pay closer attention to the prompt rather than its own internal visual priors.
It acts like a volume knob, but mathematically it's a crutch.
A crutch.
Yeah, it shifts the probability distribution to force adherence. And what the Luma AI team found is that optimal CFG actually decreases as both the model size and the training steps increase.
Okay, why is that?
Well, as you scale up a model's parameter count and it sees more data, its inherent capacity to map abstract text to visual concepts becomes structurally stronger.
So it doesn't need the extra help.
Exactly. It doesn't need the text encoder shouting at it to maintain semantic coherence. The heavy CFG crutch becomes unnecessary, which is a massive win because high CFG often degrades image diversity and introduces weird visual artifacts.
So if the model's inherent capacity to map semantics gets that much stronger just by scaling, it makes me wonder about the generation task itself. Because we know rendering pixels from pure noise is incredibly expensive.
Very expensive.
What if we strip away the generation part entirely? Does a diffusion model actually understand the visual geometry of the world, or is it just a massive texture matching engine?
The researchers tested exactly that by moving from image generation to representation learning. They ran linear probes on the frozen internal activations of the ABRA models.
Let's explain how that works for you listening. You take the diffusion model, you pass an image through it, but you freeze the model weights so they cannot update or learn anything new.
Right, you freeze the network.
Then you slap a very simple single-layer linear classifier on top of those frozen internal layers and see if that simple classifier can achieve top 1 accuracy on the ImageNet classification benchmark.
Which is a standard benchmark, yeah.
Right. And if it can, it proves the diffusion model has already extracted highly structured semantic features of the image inside its hidden layers.
And the results of those linear probes were fascinating. The classification accuracy peaked at the middle layers of the transformer network, which is consistent with where high-level semantic features generally aggregate.
Okay, that makes sense.
But critically, the accuracy peaked at a moderately high diffusion time step, specifically around t equals 0.7.
Which makes perfect mechanical sense if you think about it.
Yeah.
At time step 1.0, the image is pure Gaussian noise, so there's literally no signal to classify.
Right.
At time step 0, the image is perfectly clean, and the model is just doing imperceptible, low-level pixel denoising. But at t equals 0.7, the model is actively establishing the macro structure of the image.
Right.
It is deciding the shape, the orientation, and the core semantic boundaries. That is where the deepest understanding is happening.
Furthermore, when they mapped the scaling laws for this representation learning, they found that image understanding hits compute optimality at a much lower tokens per parameter count than image generation.
Oh, really?
Yeah, and it heavily favors increasing the dataset size over parameters.
So this goes back to the difference between discriminative tasks and generative tasks. Think of it as learning to recognize a dog versus learning to paint one from scratch.
Exactly.
Mathematically, recognizing a dog is a discriminative task. You are just drawing a boundary line in a high-dimensional space to separate the features of a dog from a cat. Your brain, or the model, requires relatively little compute to identify fur, a snout, and ears.
But generative mapping is entirely different.
Right. Taking a blank canvas of pure static and rendering a photorealistic, spatially coherent dog requires calculating the continuous probability distribution of millions of pixels. Drawing the boundaries cheap. Mapping the entire territory is incredibly expensive.
And that divergence points to a projected double point. Based on the separate scaling laws for generation and understanding, the researchers project a scale where both tasks become jointly compute optimal.
Okay, where is that crossover?
It happens around 6 billion parameters and 5 times 10 to the 22nd FLOPs.
That is massive.
It is. Below that scale, if you are mathematically optimizing your model to generate images, you are technically overtraining it for pure image understanding. But the linear probe section of the paper also gave us something profoundly useful for the actual training process.
Oh, scaling collapse.
Yes, scale and collapse.
I have to say, scaling collapse feels like a literal superpower for ML engineering.
Yeah.
Explain what this looks like when you are charting a training run.
Okay, so traditionally, we only know if a scaling law holds true after we finish training an entire suite of different size models and plot their final terminal losses on a graph.
Right. It's a retrospective analysis. You've already spent the money.
Yeah, exactly. But scale and collapse proves that the actual live trajectory of the training loss curve itself follows a universal non-power law shape.
What does that mean in practice?
Well, the researchers took the loss curves for the 60 million, 120 million, and 250 million parameter models. When they rescaled the axis, mapping the x-axis to the percentage of total training completed instead of raw steps, and the axis to a normalized loss metric, those distinct curves collapsed entirely on top of each other.
They merged into the exact same line.
Yes.
And dropping into the batch noise floor within the first 15% of the training run, regardless of how many parameters the model has, the fundamental mathematical shape of the learning process is identical if you scale the compute variables properly.
And the practical application of that universal dynamic is massive. ML engineers can now use scaling collapse as a live, real-time diagnostic tool.
This is the superpower part.
Imagine you are executing a multi-million-dollar training run on a massive frontier model. You no longer have to wait weeks or months until the end to know if your hyperparameter transfer held up or if your data mix is fundamentally flawed.
You simply plot your live, rescaled loss curve.
Right. If it diverges from the collapsed trajectory of your smaller, cheaper test models early in the run, you immediately know the run is no longer compute optimal.
You can kill a job, adjust your parameters, and save millions in wasted FLOPs.
It's a real-time safety net for frontier training.
We now have this beautifully unified theory of scaling. Optimal token ratios, hyperparameter transfer, and live-loss diagnostics. But all of this math has been built on a fixed image size.
Right.
Vision isn't static. We aren't just generating 256 by 256 pixel images anymore. What happens to the math when we turn the dial up on the image resolution? This brings us to what I like to call the resolution tax.
So to investigate this, the researchers scaled the training resolutions from 256 pixels up to 768 pixels.
Right.
The first finding seems intuitive enough. As the pixel resolution increases, the optimal tokens per parameter requirement increases significantly. It jumps from 165 TPP at 256 pixels all the way up to 247 TPP at 768 pixels.
Okay, hold on. I need to work through this because reading this part of the paper broke my brain for a second.
Yeah, it's a bit counterintuitive.
Right, because we are telling the listener that as resolution goes up, we need a higher TPP, more tokens per parameter. But the paper explicitly states that the absolute number of unique images required to reach compute optimality actually decreases at higher resolution.
Yes, it does.
How does mathematically requiring more tokens result in training on a smaller data set of images?
It sounds like a paradox, but it resolves perfectly when you look at the architecture of Vision Transformer and the strict constraints of a FLOP budget.
Okay, walk me through it.
Let's break down the information density of a single image patch. A Vision Transformer divides an image into a grid of patches, say 16 by 16 pixels.
Right, so if I have a low-resolution 256 pixel image, a single 16 by 16 patch covers a significant portion of the image. That single patch might contain an entire dog's face. It has high global semantic information.
Exactly. But as you increase the resolution to 768 pixels, you are essentially zooming in. Now, that same 16 by 16 pixel patch covers a tiny, highly localized area.
Oh, so instead of dog's face, it might just be a blurry patch of brown fur.
Yes. Because the global information density per patch has dropped, the model needs to process heavily increased numbers of patches, meaning more tokens, to extract the same amount of semantic context. You need more tokens per parameter just to learn the same concept.
Okay, I follow that. Higher resolution equals less context per patch, which requires processing more patches, driving up the required TPP. But why does that mean fewer absolute images?
Because of the attention mechanism in the transformer. As the number of patches increases, the compute required for the self-attention layers scales quadratically.
Quadratically, oh wow.
Right. Processing high-resolution images eats up your FLOP budget exponentially faster than low-resolution images. So you are chewing through your fixed compute budget so rapidly just to calculate the attention across all those extra patches that you hit your hard compute ceiling well before you've had the chance to process as many individual unique images.
So it is entirely a hardware budget constraint, not a learning capacity issue.
Precisely. Higher resolution training is completely compute-bound, not data-bound. You hit the wall on FLOPs long before you run out of unique images in your dataset.
So, bringing this all together for you listening, visual generation scaling is highly predictable, but mathematically it is a totally different beast than LLMs. Because you are mapping a continuous, noisy probability distribution, you need an insatiable amount of data, roughly 200 tokens per parameter to reach compute optimality.
But in return, you get a highly forgiving optimization surface that you can overtrain basically for free.
Which is a massive strategic win for lowering deployment and inference costs. And thanks to scaling collapse, you can monitor that entire process live.
The decoding of these dynamics is the real breakthrough here. We no longer have to blindly guess how flow-matching diffusion models will behave at frontier scales. The architectural trade-offs between FID and slick score are mapped, and the punishing compute constraints of resolution scaling are now quantifiable.
Which leaves us with a truly wild, forward-looking reality to confront. If diffusion models inherently require 10 times the data of LLMs to hit compute optimality, and high-resolution scaling is entirely compute-bound right now, what happens when the hardware finally catches up?
That's the big question.
We are going to have the FLOPs to process the data. Yep. Are we racing toward a multimodal data wall? Is it mathematically possible that there simply isn't enough clean, human-made visual data in existence to optimally train the next generation of 100 billion parameter vision models?
It's very possible.
And if we exhaust the supply of human visual data, does that effectively force the industry to train its future frontier models on synthetic slop generated by the very architectures we are trying to improve? It's a structural bottleneck that could redefine how we approach data curation. Definitely something to think about next time you prompt an image generator. Thanks for joining us on AI Paper Slop.